So in this lecture, I will speak about convergence in measure. So let us start by the definition. So we remember we have a sequence fn and a function f defined on some measurable space and taking values in the extended line. Well, I will say that fn converges to f in measure if for all epsilon positive, the measure of the set of points such that fn of x minus fx larger than epsilon converge to 0 as n goes to infinity. Okay. So to prove that fn converges to f in measure, I have to show that for any epsilon fixed, the measure of this set is converging to 0 as n goes to infinity. And let me start immediately with an example of a sequence. So this is the classical example of a sequence fn which converges to f in measure, but which does not converge pointwisely to f. And so for all x in omega, we will show that fnx does not converge to fx. And the example, it's very simple. So let me go to this new blackboard. So the set omega will be the interval 0, 1. And in 0, 1, we will take lambda as the Lebesgue measure, which is defined on the set of Lebesgue's, on the sigma algebra generated by the intervals. So let me define. Let's say at level 1, I will define a function f1 of x, which will be just equal to 1 for all x in the interval 0, 1. Then we go to level 2, and for that I will define the function f2 and f3. So f2 will be the indicator of the interval 0, 1/2. So this function f2, it's equal to 1 on the interval 0, 1/2, and it's equal to 0 on the interval 1/2, 1. And the function f3 will be equal to the indicator of the set 1/2, 1. So let me draw the picture. So here is the interval 0, 1, and here is the function f1, which is equal to 1 in the interval 0, 1. Now, for the function f2 and f3, you see that f2 is just the indicator of the interval 0, 1/2. So this is the function f2, and the function f3 will be the indicator of the interval 1/2, 1. So this is the function, the graph of the function f1, f2, and f3. And so on. So at level 3, as you may guess, my function f4 will be equal to the indicator of the interval 0, 1/4. f5 will be the indicator of the interval 1/4, 1/2, and so on. And generally speaking, at the level k, we will start with the function 2 to the power k minus 1. Right here at level 3, we start to the function 4, which is f4, which is 2 to the power 2. So here we'll have 2 to the power k minus 1, and this will go up to f2 at the power k minus 1, and these will be indicators of intervals of size 1 over 2k minus 1, right? Like in level 2, we have intervals of size 1 over 2 square. Here we'll have functions which are indicators of intervals of length 1 over the power 2k minus 1. And, well, my first claim is that this sequence of functions, so fn, I claim that fn converge to 0 in measure, and it's clear that fn of x does not converge to 0 for all x in the interval 0, 1. So let's see why it's not true that fnx does not converge. Well, you see, at level 1, if you take any point x, it's just equal to 1. Then if you go at level 2, you fix any point x, it'll be either it will be 1 for one of these functions and 0 for all other functions. So maybe this is not clear at level 3, but let me draw the graph at level 4. So at level 4 we have, at level 3, so at level 3 we have indicators of intervals of size of length 1 over 4. So this is function f4, which goes from 0 to 1/4. Then from 1/4 to 1/2 we have the function f5. For 1/2 up to 3/4 this is the function f6. And then from 3/4 to 1 we have the function f7. So you see that if you fix a point x in the interval 0, 1, so we will observe the function f4 at point x, f5 at point x, f6 at point x, and f7 at point x. So for any x, what I claim is that for 3 values of k, that these numbers will be 0, and for one of them it will be equal to 1. If we chose x in the interval 1/4, we will have 1, 0, 0, 0. If we chose x in the interval 1/4, 1/2, it will be 0, 1, 0, 0, and so on. So if we go through this sequence, at any level, fk of x will be equal to 1 for one of these k's and 0 for all the other. So we have here, as we can construct for any x, a subsequence k going to plus infinity, for which fk of x is equal to 1. And it's also very easy to construct a subsequence fk, for which fk of x is equal to 0 for any k. So this proves that statement that for any x in this interval 0, 1, it's not true that fnx does not converge to 0. Now let's see that fn converge to 0 in measure. Well, to prove that, so let me erase the first 2 lines. By definition, we have to estimate the measure of the points x such that fn of x minus the limit, which is 0, it's larger than epsilon. Okay? So we fix an epsilon positive, and we have to prove that this sequence converges to 0. Well, but what I claim is that, of course, we can, if epsilon it's larger or equal to 1, then this measure it's always equal to 0, because fnx takes values equal to either 0 or 1. So if epsilon is larger or equal than 1, so this is always equal to 0. So there is nothing to prove. So we can assume that epsilon it's contained between 0 and 1. And in this case, well, let's assume that we take an integer j, which belongs to the level k. This means that j is between 2k minus 1 and 2 to the power k minus 1. Well, if j belongs to this interval, f of j, it's the indicator of an interval of length 1 over 2k minus 1. Right? Which means that for j in this interval, the measure of this set is the measure of the points x for which fj of x is equal to 1, but fj of x is equal to 1 on an interval of length 1 over 2 to the power k minus 1. So the measure of this set, it's exactly equal, so for j belonging to the level k, this is exactly equal to 1 over 2k minus 1, because this is exactly the length of the interval in which fj is equal to 1. Well, but this is less or equal. You see, I need a lower bound for 2k minus 1, but 2k minus 1, so I can write this object as 2 times 2k minus 1, and this is bounded by 2 times 2k minus 1. So 2k minus 1, it's bounded below by j over 2. So this object, it's bounded above by 2 over j, and here I'm taking j in this, so I'm considering here in fact fj. So what we proved is that for any j, the measure of this set, it's bounded by 2 over j, which indeed converges to 0, and this proves therefore that fj is converging to 0 in measure. So we have here an example, well, the classical example, of a sequence of functions fj which converge to 0 in measure, but which does not converge to 0 pointwisely. And well, this is an example to keep in mind. And what's happening here is that, well, these sets are changing, but what's important is to estimate not the set in itself, but the measure of the set. And this is, it comes from this fact, the fact that we're only estimating measure of sets, that we may have a sequence which is converging to 0 in measure, but which is not converging pointwisely to 0. So it's important to keep in mind this, this example. So after the definition of the example, I want to make 2 observations, which are very simple. The first one is that, well, assume that we have a sequence fn, which converges in measure to a function f. So let me represent from now on convergence in measure by this symbol. And let's assume that fn, it's also converging to g in measure. And what I claim is that this implies that f is equal to g almost surely. Okay. So convergence in measure characterize the limit. And to prove that f is equal to g almost surely, what I will do is I will estimate the set of points for which fx minus g of x is larger than delta. So I'll fix delta positive, and I will estimate this difference. Well, so I will introduce here minus fn of x and plus f of x, and what I'm saying is that if this difference is larger than delta, then either f minus fn should be larger than delta over 2, or g minus fn should be larger than delta of 2 over 2. So this means that this set, the measure of this set, is bounded by the measure of the sets of point x, such that fn of x minus f of x is larger than delta over 2, plus the measure of the points x, such that fn of x minus g of x, it's larger than delta of 2. And, well, since fn is converging to f in measure, we have that the measure of this set is converging to 0 as n goes to infinity. And in the same way, since fn is converging to g in measure, the measure of this set goes to 0 as n increases to infinity, which means that the measure of this set converges to 0, but it doesn't depend on n, so this means this bound implies that this set has measure 0. So this set has measure 0 for all delta, so I can take now delta equal to 1 over k, so the measure of this set will be equal to 0 for any k, so I can get the union over all k. The measure of the union over all k will be still equal to 0, and the union over all k of this set, it's the set of points x for which fx is different from gx. So this set has measure 0, and therefore f is equal to g almost surely. So that's also very important. If you have a sequence which converges to two different functions, they must be equal almost surely. The second simple observation is that convergence in measure, it's a property of class. What I want to say is that if you have a sequence fn which is converging to f in measure, and if gn it's equivalent to fn, which means that gn it's almost surely equal to fn, and if g it's almost surely equal to f, then gn is also converging almost in measure to the function g. And this is also a very simple observation. So in order to show that gn converges to g in measure, we have to estimate the measure of the sets of points x such that gnx minus gx it's larger than epsilon. So we fix an epsilon positive, and we want to estimate the measure of this set. Well, let me call En the set of points for which Gn is equal to Fn. E0 the set of points x for which Fx is equal to Gx. Let me call E the intersection of these sets. Intersections of the sets En. So what I know is that the measure of E complement it's equal to 0, right? Because, well, E complement is the union of the complements, and the complements of these sets have measure 0 because they are all almost surely equal. Now we can decompose this set according to E and E complement. Well, E complement, the measure of E complement is 0, so this is less or equal than the measure of this set intersection E. But on E, we have that Gn it's equal to Fn, and G it's equal to F on the set E0, therefore on the set E also. So this is, okay, so let me write it what I'm doing. I'm first claiming that the measure of this set it's less than or equal to the measure of points x such that Gn minus G it's larger than E intersection E. But on the set E, which is the intersection of the set En, I can replace Gn by Fn and G by F. So this is equal And now I can bound that by the measure of the same set without intersection E. And for that set, since Fn is converging to F in measure, this goes to 0. And therefore, this proves that Gn is converging to G in measure. Okay, so this proves my claim, which is stating that convergence in measure, it's a property, it's a class property. You can take any function in the equivalent classes and you get the same result. The concept of convergence in measure is very important. It will appear many, many times when proving convergence of functions. So now I will state two important results which connect convergence in measure to almost sure convergence. So my first lemma is the following. Well, assume that you have a sequence Fn which is converging to F in measure. And my claim is that then I can find a subsequence Nk which converge to F almost surely. So I claim that there exists a subsequence Nk such that F Nk converge to F almost surely. So it's clear that Fn converging to F in measure cannot imply that Fn converge to F almost surely. We've seen an example in which we had convergence in measure and we didn't have convergence, pointwise convergence. But now what I claim is that, well, we can now choose a subsequence which converge almost surely. So before I prove that this lemma, let's go back to example I presented and let's construct in that example this subsequence. So remember, our first function was a constant function equal to 1. The second function was equal to 1 on the interval 0, 1/2, and then equal to 1 on the interval 1/2, 1. This was what I call level 2. Then at level 3, I had functions which were equal to 1 on intervals of length 1/4. And so on, till the one which was equal to 1 on the between 3/4 and 1. So, and this was what I called level 3. So in order to, now I want from this sequence construct a subsequence which converge to 0 almost surely. And what I will do is at each level choose the first function. So here is my function, so here is N1, so that will be first function of my subsequence. So that will be my second function. So at level 2, I chose the first one. So now I go to level 3, and at level 3, I choose the first one, which is the one which is equal to 1 in the interval 0, 1/4. So let me write what will be the first function at level 4. So the first function at level 4 will be the one which is equal to 1 in the interval 0, 1/8, and so on. So you see, well, that this function, this subsequence which I'm constructing, is indeed converging to 0 actually for all points but point 0, right? So the kth function of my subsequence will be, so let me just say, well, so this is the function 1, this is a function 2. So let me call G the subsequence which I'm constructing. So this is G1, this is the function G2, that will be my function G3, this one is G4, and the function Gk will be the function which is equal to 1 from 0 to 1 at power divided by 2 k plus 1. Right here I have k equal to 2 and I get 2 to the power 3, so here k will be jk plus 1, and therefore, well, it's clear that this sequence gk of x, it's converging to 0 for all x different from 0. So we construct in our example a subsequence of the original sequence which is converging to 0 almost surely for almost all points. Okay, so well, at least this statement holds for the example I presented. So now let's give a proof of this result. So proof. Right. So what we know is that Fn converges to F in measure. This means that for all epsilon positive, the measure of the points x such that Fnx minus Fx is larger than epsilon, that these converge to 0 as n goes to infinity. So just to avoid writing Fnx minus Fx, let me call this function, this difference, Gnx. And what I want to prove is that Gn, it's converging almost surely to 0 from the fact that it converges to 0 in measure. So I want to, from Gn, construct a subsequence, Gnk, which converges to 0 almost surely. Well, so if I take epsilon equal to 1 over k, I know that this sequence with epsilon equal to 1 over k, it's converging to 0. So I can find nk, for which the measure of the points x such that Gn of x larger than 1 over k. I know that this sequence it's converging to 0 as n goes to infinity, so I can find nk for which this sequence it's smaller than 1 over 2 multiplied by 1 over 2 to the power k for all n larger than nk. Right, I know that this sequence is converging to 0, so it will be smaller than this value for n sufficiently large, for n larger than nk. So in particular, I can find a sequence nk which is increasing, so I want just nk to be smaller or equal to nk plus 1, such that the measure of x such that Gnk of x larger than 1 over k, so that this is smaller than 2 to the power k plus 1. Right? So I just construct n1, n2, and once I have defined n1, n2, and k minus 1, from that estimate I can find nk larger than all previous ones for which this is true. So I can indeed construct this sequence which is increasing and for which that inequality holds. So let me continue on the next blackboard. I will just repeat what I wrote here, which means that I construct a sequence nk, which is strictly increasing, and for which the measure of the points x such that g nk of x larger than 1 over k, this is bounded by 1 divided by 2 to the power k plus 1. And I chose here 2 to the power 2k 2 to the power k plus 1 just to get now the union. So the measure of the union of k larger than k0 of the points x such that g and k x larger than 1 over k. So the measure of this union, it's less than or equal to the sum of these measures, and the sum for k larger than k0, this is bounded by 1 over 2 to the power k0. So this means that now I can take the intersection over all k0s and get that if I take the intersection of all k0 larger than 1 of this union, well, this measure, it's bounded by that one for any k0. So this measure, it's bounded by 1 over 2 to the power k0 for any k0. So this measure, it's in fact equal to 0. Right? This measure, it's contained, this set, it's contained in that one for all k0, which means that the measure of this set is smaller than this value for all k0, which means that the measure of this set has to be equal to 0. So this is my set E complement. So the set E complement has measure 0. So now I have what I claim is that on the set E, so if x belongs to E, what I claim is that G and x, k, converge to 0. So let's take a point x in E. Well, since x belongs to E, it belongs, well, I have to write before continuing, I have to write what is the complement of this set, right? So let's write here on the first line what is the set E. So the set E is the complement of this set. So it's the union for k not larger or equal than 1, the intersection of k larger than k naught of the complement of this set, so point x, such that g and k of x, it's less or equal than 1 over k. So here's my set E. So let me go back. I want to show that for any point x in E, the sequence g and k of x converge to 0. So let's fix a point x in E. It belongs to this set. So it means that it belongs to this union. So this means that x belongs to one of these. So there exists a k0 for which x belongs to this intersection. So there exists, this implies that there exists k0 such that x belongs to this intersection. So since x belongs to this intersection, this means that it belongs to all. So this means that for all k larger than k naught, g and k of x, it's bounded by 1 over k. And since this holds for all k larger than k naught, and since this sequence is converging to 0 as k converges to infinity, this means that g and k of x indeed converge to 0. And this is exactly what we wanted to prove. So we proved the existence of the set E, which has two properties. On the one hand, the measure of the complement of E is 0. And on the other hand, for any point x in E, the sequence g and k of x converge to 0. This means that g and k converge to 0 almost surely. And this is exactly what we wanted to prove. We proved the existence of the subsequence g and k which converge to 0 almost surely, and this proves the lemma. Now, let's discuss the converse. So I have a sequence fn which converge to f almost surely, and I would like to see if this entails the convergence of fn to f in measure. So I want to discuss these converse. Right? We have seen that if fn converges to f in measure, well, it's not true that it converges to f in almost surely, but we can find a subsequence for which this is true. I want to discuss the converse. Well, here is an observation, well, more an example. So I'll give you an example of a sequence which is converging almost surely to 0, but which is not converging in measure. And the example, it's obvious, it's very simple. So consider the function which is equal to 0 up to n, and then which is equal to 1. So here's the graph of the function fn. The function fn is equal to 0 up to n, and then it's equal to 1. So it's clear that fn is converging to 0 almost surely. In fact, it's converging to 0 pointwisely. However, if I consider the Lebesgue measure defined on the line, the Lebesgue measure of the points x such that fn of x, it's say larger than epsilon. If I take epsilon between 0 and 1, well, the measure of this set, it's equal to plus infinity, right? Because this set, if epsilon is between 0 and 1, this set corresponds to the set n infinity. And therefore, the measure of this set, it's plus infinity. So it's not true that fn is converging to 0 in measure because, well, this sequence is not converging to 0 for epsilon between 0 and 1. Well, so this statement, as it is written, it's not true. Of course, here, what is providing this example is the fact that the measure of the space, it's equal to plus infinity. So let us add an assumption to turn this statement into a lemma. We will assume that the measure of the space is finite. So assume that the measure of the space is finite, then I claim that if you have a sequence fn converging to f almost surely, then it's true that fn converges to f in measure. And the proof, well, the proof will use a fact that we already proved. We have seen that if the space has finite measure, and if we have a sequence fn converging to f almost surely, then Fn converge to F almost uniformly. So let me remember what it means. It means that for any positive epsilon, you can find a set E epsilon such that the measure of the complement of E epsilon is bounded by epsilon, and Fn converge to F uniformly on E epsilon. Right, so this is the definition of almost uniform convergence, and we have seen in the previous lecture that if we have a sequence converging to F almost surely on a space whose total measure, whose measure is finite, then we have almost uniform convergence. Well, once we have almost uniform convergence, we have now to prove that this almost uniform convergence entails convergence in measure. So for convergence in measure, what we need to prove is that the measure of the points x such that Fnx minus Fx it's bounded by epsilon, that this converges to 0. So this is what we need to prove. So to complete the proof, let me erase this piece of the blackboard, which I will not need anymore. So what we need to show is that this converges, so that this measure goes to 0. To show that this measure goes to 0, fix epsilon. What we have to prove is that if you fix some delta positive, we have to show that there exists some n which depends on delta, such that for all n larger than n delta, the measure of the points x such that Fnx minus Fx larger than epsilon is smaller than delta. So this is what we need to prove. Okay, so given that delta, so here epsilon I will take as epsilon delta. So given that delta, I know that there exists a set E which depends on delta, such that, well, the measure of the complement of E delta, it's bounded by delta. And I know also that Fn, it's converging to F uniformly on E delta. Well, since Fn is converging to F uniformly on this set, this means that, well, given epsilon, given this epsilon, I can find n which depends on that epsilon and this delta, because I know that the convergence is uniform on that set, so it depends on this set, such that if n it's larger than this n which depends on epsilon and delta, then the supremum over x in this set E delta of f and x minus fx, so this supremum, it's less than epsilon. Okay, this is the existence of this integer n, which depends on epsilon and delta, comes from the fact that you have uniform convergence on this set. All right. So this means that if you take any n larger than n epsilon delta, you can estimate. So remember that now I obtain my n delta. Right? I obtain my n delta, And now I have to prove that for any n larger than this number, this measure is bounded by delta. So let's estimate the measure of that set. So let me repeat what is this set. This set is the set fnx minus fx larger than epsilon. Well, I will estimate the measure of this set by taking the intersection of this set with the set E delta and with the complement of the set E delta, and I will get an upper bound if on the second term I just estimate everything by the set E delta complement. Well, but we know that the set E delta complement has a measure bounded by delta. So this expression here, it's bounded by delta. On the other hand, well, on the set E delta, I know that the supremum, if I take n larger than n epsilon delta, if I take n larger than this number, this supremum is bounded by epsilon. So, on the set E delta, if n is larger than this number, fnx minus fx, it's smaller or equal than epsilon. So the intersection of these two sets is empty, and therefore the measure of this set is equal to 0. And this proves, therefore, that the measure of this set is bounded by delta, which is exactly what we wanted to prove, and this completes the proof of the lemma. So let me just recall the statement of the lemma. The lemma was asserting that if you have a sequence fn converging almost surely to a function f, and if the space omega has finite measure, then fn converges to f in measure. And this completes this lecture.